Alrighty, so 3.6, this is kind of a building block section that's setting up future chapters. So we're talking about functions here. And we have 4 objectives. The first is to define relation, domain, range, and then functions. And after that, this is kind of the big thing, is to be able to identify a function. I want to be able to look at something and determine or decide whether it's a function or not. And so one tool that we have to do that is called the vertical line test. Or VLT for short. And then our final objective is to look at what we call function notation. So starting out with relations, a relation is a correspondence between 2 sets, an input set and an output set. We see these as equations most often in math, but we can also represent relations as tables, graphs, ordered pairs, verbally written down, just describing a relation. A relation is a really basic concept, and to be quite honest, math kind of steals this just from the English definition of relation. A relation is just an association, essentially, between 2 sets of things. It doesn't really have much rules after that. Now, with relations comes domains and ranges. So if we think of a relation as an ordered pair, then the domain of the relation is the input set, or the set of all the x components of those ordered pairs. And the range of the relation is the output set, or the set of all the y components of the ordered pairs. So to make that make a little bit more sense, we have this example here. So determine the domain and the range. So the domain is the input set or the x components. So our domain as a set always has a curly brace, is all the x pieces of all of these points. Now, when you have 2 like this, you don't repeat. We don't need to list them more than once. So this is 2, 0, and 3 is our domain. And our range is all the y pieces. And again, when you have 2 that repeat, you don't need to list them twice. You just list them once. So this is 3, 4, and -1 is our range. So that's the basic form of relations. Now what we really want to get to is functions. So functions are relations first and foremost. So that's a big important thing. They are relations. They're a correspondence between a domain and a range, an input and an output, in which each input value corresponds to exactly 1 output value that's associated with it. And so this is a big deal. A second ago, I said that relations don't really have any rules to them aside of general association between its domain and its range. Functions do have this rule. They have to always satisfy this rule. 1 input or 1 output for each input. So you can't have 2 outputs that have the same input. So if you look at this example here, this point and this point have the same input, which means that there are 2 outputs for each input, or for this input. Now, this is easy to see when you have it listed in ordered pairs like this. So what we're going to do, if we turn the page here, is look at some not so easy things, starting, well, we're going to start easy and then build our way into more difficult ones. And then we'll look at how we can actually identify functions from graphs using the vertical line test. So we're going to determine whether the following relations are functions. So starting with A, this is the previous example. There are two 2's here. That means that our input repeats, and so this is not a function, since 2 has more than one output. Now looking at B, our x's are all different, so that means that this is a function. No repeated x values or inputs. Now some of you might be thinking, well, what about if we repeat a y value? Well, repeating the y value is actually not a problem, because you can have multiple y values. They can all be the same y value. It's the inputs that are the problem. And when we get to the vertical line test, we'll be able to see geometrically why that is. So now looking at C, the age of each person to the nearest year. So that takes people and connects it to their age. So now the question is, can you ever have a person with two ages? Right, that would be having one person, one input, with more than one output. And the answer here is no, you can't have two ages if you're a person. So this is a function as well. No person can have two ages. So looking at D through F, these are equations now. These become more difficult to see. And so what you have to look at is, can you plug in an x? Is there an x that gives two answers? So is there a number that when you multiply it by 3 and add 1, you can get two different things? Well, for multiplication and addition, the answer is no. So that means that this is a function. But you can see that that's a little bit harder to wrap your mind around than some of these more straightforward examples in A through C. So now when we look at E, we ask the same question: is there an x value that gives two answers? In other words, is there something that you can square that will give you two answers? If you square a number, does it have two possible answers? And that is also no, there is not, so this is also a function. And then F says, is there an x that can give you two answers that looks like y squared? Well, as it turns out, there is. So what if x is 4? Well, 4 equals 2 squared, and it equals negative 2 squared. So that means there are two y values associated with this x value of 4. So in F, this is not a function. Now some of you might be saying, that's way harder to do than the first three, and it is. Looking at equations and determining if they're functions or not takes a little bit more understanding of what those equations are doing, whereas here you can see it listed out, 2 and 2, no repeated, and then this is a very conceptual question in part C, but we can break it down simply: people can't have two ages. So to help us with that, with the equations, we have the vertical line test. So we use the vertical line test to determine whether a graph is a function. So if you can graph an equation, you can figure out if it's a function. And what the vertical line test says is, if no vertical line can be drawn so that it intersects a graph more than once, the graph is a function. If even one vertical line intersects more than once, the graph is not a function. And you don't have to find all the vertical lines that intersect more than once. You just have to find one to prove it's not a function. So we're going to look at specifically lines, this type of function, and this type of function. Well, I should say equation, not function for that last one, to see geometrically why they're not functions using the vertical line test. So if we start with our line, so that's what we're doing in this example. We're going to use the VLT to determine which of the following are not functions. So our line looks something like this. And if I were to try and draw vertical lines through this line, no matter what vertical line I picked, pretend that these are all vertical, by the way, I could only ever cross once. And it doesn't matter how many different lines I try, this is always going to be true. So this would be a function, which is exactly what we set up here in part D. The line is a function. Now for part E, this is a quadratic, which we'll be studying more in the future. And this looks like this. So now if I try and draw vertical lines, again, pretend that these are actually straight lines. No matter what I do, once again, it's still only going to cross one time. None of these lines will ever cross again. And even if we continue drawing this up and up and up, each line will only cross once. So this is also a function. Just like we saw. And so now if we look at the last one, x equals y squared, well, this is a sideways parabola. And so now you can start to see the issue at, let's say, x equals 4, because that was the example we used. At x equals 4, we're going to cross twice here. This being at -2, and this being at 2. And so that means there are two x's, or two y's for the same x. We fail the vertical line test. And we fail in a lot of other places too, right? We fail here, and we fail here, and we fail here. In fact, you fail on every single vertical line you can do except this one right here. But it doesn't matter, because our definition says is if even one vertical line intersects more than once, it's not a function. So you only need to find one failure to be not a function, even if you are 99.99% passing the vertical line test, except for one location, you still fail. Right? It's an all or nothing type of test. So this is not a function. And the last type of graph I want to show you is a common graph that you're going to study a lot, and that is a circle. It's one of my better circles. I'm pretty bad at drawing circles. And we can see that the circle also is not a function, because it's going to fail that vertical line test. Now, even when we have things that aren't functions, like x equals y squared and the circle, we still study these things in math because they're still interesting. They still can be used to model stuff. But typically what happens is we have to split and look at these in a very specific lens. So to look at the circle and consider a circle as a function, to do some functional analysis, what if we only look at half? That half's a function. Similarly, we could look at the other half, the bottom half. That half is a function. When we put them together, we lose function. We lose the definition of the function. We fail the vertical line test. So that's how we can study things that are not functions as if they were. It makes it really easy to apply all the definitions that we will use for functions to things like this graph and the circle, even though we know they're not functions. So that's the vertical line test. You just have to find one place. You don't need to find a bunch, just one that fails, and you're not a function. So the last thing in this chapter that we're going to talk about is function notation. This is how we talk about and write functions. So distinguish functions from just regular old relations, because again, you look at these equations on their own without all of our work, specifically these two here, they're just equations. They're very, very similar. So we want to distinguish them in some way. We say if a relation y is a function of x, we denote it as y equals f of x. And this is read as y equals f of x, just like I said it. Not f times x, not fx, not f. Some people just say f, x, none of that. It's y equals f of x. This is an argument. F is a function. And this notation means that y specifically depends on x. It's what we call the dependent variable. And that dependency is named f. F is a name, it's not a value. And because of this, we call, like I said, y the dependent variable and x the independent variable, because x can change, but y only changes when x changes. So when we're working with function notation, finding function values is the most common thing that we do. And so that's what this next example is all about. So finding function values of g of x equals 3x squared minus 2. So g of 1, the way that this works is you replace the x with a 1. So you have 3 times 1 squared minus 2. So this is 3 times 1 minus 2, or 3 minus 2 equals 1. And that's our function value, g of 1. So you would say g of 1 equals 1, or the point 1 comma 1 is on the graph of g. Part B, plugging in 0, g of 0. This equals 3 times 0 squared minus 2. This is going to be 0 times 3 is 0 minus 2, or just negative 2. And so that means that g of 0 equals negative 2, or negative 2 comma, 0 comma negative 2 is on the graph. Part C, g of negative 2. So this is where you have to be careful when you're plugging numbers in for x. You have to make sure that you plug them in perfectly as they're seen. So everything that's inside these parentheses is what replaces x. So that includes the negative, so we want to put parentheses there. And so this is 3 times 4 now, minus 2, or 12 minus 2, which equals 10. And so our g of negative 2 equals 10, or negative 2 comma 10 is the point on our graph. Running out of space here, so I'm not going to write that part, but just like we did here. 1, 1 is on the graph. This means that negative 2, 10 is on the graph of g. And I'm going to turn the page here to the back side to do the final two. So that was C, so this is D, g of A. I'm just going to rewrite g of x here. It's 3x squared minus 2. So g of A equals 3 times a squared minus 2. Now we don't know what a is, so this is just 3a squared minus 2. That's what g of a is. Sometimes you plug in unknown variables. And the point is the point a comma 3a squared minus 2. Now this doesn't tell us anything more than x, because we just swapped out x's for a's. But you can still plug in values like that. And then finally we have g of x plus h. So this is 3 times the quantity, x plus h squared minus 2. Remember, this is one of our special products, perfect square trinomial, so this is 3 times x squared plus 2xh plus h squared minus 2. And then we distribute our 3, and we have 3x squared plus 6xh plus 3h squared minus 2. And that's g of x plus h. So we've taken it and actually made it more complicated by adding this second variable. So the big takeaway here with this example is whatever you see inside these parentheses goes in the entire place of x. It's not just what's different. It's not just what's easy. You have to make sure that you are swapping in exactly what's written here in the place of x in your formula from here. Okay, so I know we're at 20 minutes here. The last little definition is linear function. And we're going to be talking about linear functions more in later chapters. But I just want to introduce it here. So a linear function is a function, so it satisfies our definition. It passes the vertical line test. And its function notation is f of x equals mx plus b. So as you can see, this looks just like a line. We've basically swapped out the y here, put that in parentheses, y equals f of x. That's what our definition of function says. Right, y is f of x, so we replace y with f of x. And there's no difference in terms of how we graph linear equations or linear functions. We use all the same techniques that we've seen in the previous sections to analyze linear functions, to graph linear functions, and to work with linear functions, just as we did with linear equations. So there's, and I can't stress this enough, literally no difference between a linear equation and a linear function, because every linear equation is a function by definition. Okay, so that's the end of chapter 3 for us.